Alright, enough algebra. Let's try and work out what on earth a complex number might have to do with the real numbers that you've been used to before. So let's take you back to being a baby. You learned to count, you learned that 1 was followed by 2, was followed by 3, and eventually you need to put them on a line and to count along it. And at some point somebody told you that you could count below 0 and that these numbers existed too. And that was all fun and dandy. And then maybe you had someone who explained that the fractions were in here somewhere, and there were some numbers in here that weren't even fractions, but they're on the number line. You know, pi is here somewhere, it's 3 and a bit. There's pi having fun. You know, this is 3 halves. The square root of 2 is down here somewhere. These numbers are on the number line somewhere. But where on earth is I? Where on earth is 2 plus 3i? What about negative 1 take 3/4 of I? Where are they? Well, these, what we need to remember is that if I change the real part, I can have 3i added to any real part. So I can change this part independently, and I can also change this part independently. So I need a system which is joined of 2 independent things. Some would recognise that as the definition of a scatter diagram, which is obviously just a coordinate plot. So if we add a perpendicular number line over here, we can call this I, and we can call this 2i, we can call this 3i, and so on, and this will be negative I, negative 2i, negative 3i. So that means that I is just here on the number line, and that 2 plus 3i is 2, and 3i is there on the number line. That is 2 plus 3i. Of course, it's no longer a number line, it's a plane. And that's always been there, it turns out. So the complex numbers exist just in this kind of space. And everything you know about real numbers is still on this plane, it's just on this one line. And the plane just allows us to think about how these other numbers interact. And we'll get to interpreting it, but that is this is called an Argand diagram. This is the real axis, this is the imaginary axis, and every complex number is somewhere on this plane. Just like every real number you've heard of before, was on this line somewhere. Alright? Now that actually allows us to think about numbers in 2 ways. This looks like Cartesian coordinates, so we often call this form the Cartesian form, where we have the x part and the y part if you're being layman with the terms, but the real part makes part explicit. There's another way of describing where this place is. This is a real place on the number line. If you start at the beginning, it's over there, and it's that far away. Okay? So as well as having this description, there's another description of this number. We can describe its angle, theta, given in radians, so you'll have to learn what those are, rather than degrees. And we describe how far away it is, and we call this the modulus, the absolute size. So if we take this example, 2 plus 3i, and we call that z, the modulus of z, the size of z, is just Pythagoras. This is how we do distance before. 2 squared plus 3 squared, all rooted. So that's going to be root 13. So that's root 13 away from the origin, just like 3 is 3 away from the origin. But it's no longer along the number line, it's been rotated up a bit. It's at this angle. Well, a bit of trigonometry tells us that's going to be something to do with tan, because it's got the opposite and the adjacent that we know. So the inverse tan of opposite over adjacent will give us, if we whip out a calculator in the right mode, so our angle here needs to be measured in radians, not degrees, so I need to change that to radians, which we'll do in a separate course at some point. It's just an angle measure, and we get 0.983 radians. So that means that z is root 13 at an angle of 0.983 radians. Okay, that's lovely.